Hey guys, how's it going? My name is John and you're watching Soul Encoded. Today I wanted to solve another Leetcode problem. It's one of the most famous problems that you'll ever solve, essentially. The problem is called binary search, and without further ado, let's dive into the problem. So I'm going to quickly read the problem. I wanted to spend some time talking about a few things before we actually get solving the problem. But let me go ahead and introduce the problem to you guys. So, given a sorted in ascending order integer array numbers of n elements and a target value, write a function to search targets in the number. If the target exists, then return its index. Otherwise, return -1. So this problem seems like super simple, right? You're basically given like an array, and then you have some target value that you need to find in the array. Immediately, the obvious answer to this question is by simply just iterating over the nums array, and just for each index item, just check if that item exists, if the target value exists, and then return that index. And after it goes through the entire array, then you can return -1 if it doesn't. So it will look something like that. This is not the answer, obviously. I is less than nums.length. I plus plus. So you could do nums. So if nums I equal the target, then you could return I, else return -1. So this simple implementation that you see will actually, it's a valid solution for this particular problem. But before we move on, this is obviously not the correct answer for this particular problem, but I wanted to briefly stop and explain a concept to you guys. The reason why I chose this particular problem for today is because it is a great way for me to introduce the topic of big O notations. Big O notation is a mathematical term that kind of describes the limits of a particular function. And in programming, the hard thing about programming is not necessarily finding an answer that works, but finding the right answer. So oftentimes you'll hear this a lot when people say, you know, engineering is all about making trade-offs. And I wholeheartedly believe that this is the case. Oftentimes you will start working on a project, and then there's a million ways to do an implementation, but you need to look at what the business requirements are, and then you need to make necessary trade-offs in your tech stack or your implementation or what have you. And the reason why we're looking at this problem and we're talking about big O here is because when you're starting to work in these problems, you're going to have to understand what big O notation is, especially when it comes to time complexity and also space complexity. Like, those are like the two most important things. So if you look at this example that we wrote here, this is what you call n time complexity. The reason why it's n times is because this program will take linear time, essentially, n times. It will grow, it will take as long as the input size, essentially. But let's say that you did something where you had like a nested for loop here, something like that. Obviously, I'm not solving the problem at this point. Something like that. So just by having this nested loop, now this becomes an n square problem. So having a firm understanding of big O notation, it's a super important skill for you guys to have. So understanding big O is actually really important when you want to start analyzing your program. If you don't have a firm understanding of the code that you write and what kind of time complexities or space complexities it has, then how can you even make trade-offs or think of different implementations that are better? You can't really justify that unless you have like a good way to analyze your code. So I'm gonna delete this. Binary search is one of those classic problems that you'll learn in programming. It's under the search family of algorithms. And binary search is it's a great algorithm to learn because it's one of the first algorithms where it introduces the concept of having your input size on every iteration. And hence it becomes like a log n lookup for big O notation wise. and that means that the curve kind of looks like this, and then like tapers off, and that means that because the input size is like halving every time, you're kind of guaranteed for somewhat of a fast program. Just to give you guys a comparison, I said that the first implementation that we did, it grows linearly, but if we have another one that grows at a log n pace, then eventually the log n implementation will be a lot faster at like a larger input size than if it were to grow linearly, right? I'll go into another entire video and give Big O like the time that it needs, but I just wanted to start introducing this kind of concept to you guys, because just solving these Leetcode problems is, you know, it's great. Like, oh, I got the answer, I got the like one-liner answer, but it's usually not the point of doing these. Like, that's not the point of solving these problems. The real point is to look at this problem and try to solve it in the most efficient and clean and understandable way as possible. And that's all really programming and engineering is. So you're just trying to solve a problem in a way that meets business requirements, and it's clean and readable for other humans, essentially. So I know that was like a long introduction to this problem, but I just wanted to like kind of lay out the foundations of this topic for you guys. But yeah, let's dive into this problem. So the obvious way I already described is that you just iterate through all of the numbers here, and then you check every number. But one key thing about this problem is that the input that we're given is sorted. Now, this is a good tip when you're solving these problems. They often won't just give you a sorted like array for no reason. Like, there's a reason why it's sorted, and that's because binary search assumes that for binary search to work, you have to have an input that is sorted in some format. So the way we're gonna solve this problem is by essentially starting with a left, and then we're starting with a right, and then so this will be the beginning of the input, and this will be the end of the input. And then for every iteration, we're gonna ask the program, hey, check right in between, right in the middle of these two, is this the target value? And then if it is, then return that index. The next thing we need to do is say, hey, if it's not that, is the target value like larger than the current value in the index? Then I always have to think about this a little bit, but like, so basically if the current number, the index that you are, is less than the target, then you need to move your left up, right? And then that becomes a new lower bound, and then you keep the right bound, and then you ask that same question one more time, and then you keep doing this thing where you're like changing the lower bound and upper bound, and then eventually you'll either where the lower bound and the upper bound will meet, and then you will just either find the point, or you will say, hey, it's no longer in there, I've exhausted everything. So that's what we're going to do. So let's go ahead and program that now. There's also two ways to solve this. I'm going to show you guys both ways, and by that I mean an iterative way and a recursive way. So let's do the iterative way first. So I'm just going to say let left equals 0, and let right equals nums.length -1. You got to do -1 here because index starts at 0, but length is like, it gives you like the count of it, so it actually the length starts at 1. So you have, if you want to get to the last index, you have to actually subtract by 1 here. That's just like a JavaScript thing and most programming languages. So here we're going to do a while loop, and then we're going to say if left is less than or equal to right. So here all I'm saying is just continue running this while loop until the lower bound and then the upper bound, essentially the left and the right, meets. Right, and if we don't do that, this is our like base case essentially to exit out. We did not find the target value. And in here we're gonna just do, the first thing is we need to find the mid value. This can be a little bit tricky, but the way you could, so like if obviously if you have like the left and the right, then you could just find the middle, right? So you could just say right divided by 2. But because we're going to be changing the left and right bounds constantly, we need to be a little bit like a little bit more clever when we do this. The way I like to do it is the way I like to think about it is I'll take like the right. So I take what the right index is. So let's say that's like a 5, and then I'll subtract that by the left. So now this gives me the like total values of how many like items that are left. So that'll be like 3, right? If it was like 5 and then like 2, for example. And then you need to math out for this or round this, because if you don't, that could be like a decimal point, so you just want to round that up or round that down in this case. And then you want to add this whole thing, you want to add left to this whole thing. So what essentially you're doing is you're getting the difference from like the upper bound and then the lower bound. So that gives you the total, like, and then you're dividing that exact amount. So you're saying, oh, it's like 2, let's say, and then you take what was there on the lower bound and you add it up, and that gives you the midpoint. That's something that you might like have to think about in your head for a little bit, but it's probably like the hardest part about this program. So the next thing is, like I said, we're gonna look at the item that we're currently in, which is mid, and then we're gonna ask if that is equal to the target. If it is, then super simple, we're just gonna return mid. Now mid, I have to remind you, it's the index, right? So the next thing is we're gonna say else if we're going to check if nums mid is greater, or this could be either way, greater than the target. So I guess less than the target. So this, what I mean by you could do either way is because if the current mid is less than the target, then we know that our upper bound has to be reset to something that's like lower than the mid. So in that case, that would be right equals mid minus left, and left equals mid plus right. I might have like reversed these, but this is like super easy. Like once you like run it once, you'll know if you messed up or not. So what I'm doing here is essentially I'm just resetting the lower bound and then the upper bound, the left and the right, over and over again until they meet right in the middle. So one really interesting benefit that this has is, as I mentioned, every iteration of this while loop, you're literally because you're cutting the input size by half. That's why it's log n, because you're cutting the input size by half every time. So yeah, and if that doesn't work, then we'll return 1. So let me go ahead and run this. Hopefully I didn't mess anything up. I definitely made an error somewhere because this is wrong. So let me debug that real quick. Okay, I reversed these two. So yeah, like I said, like usually when I'm thinking through this, I could do it in the first try, but because I'm like speaking, it's hard, guys. It's hard. Give me a break. Okay, so it looks like our tester was successful. Let's run this whole thing, and it was accepted. So great. So that's awesome. So this is the iterative way, and just for funsies, let's delete this whole thing, and then let's do it recursively. So same setup here. Equals 0. Goes nums.length minus 1. And then let's create another function down here. We'll call it BSC for binary search. And I know we're gonna need a left, and we're gonna need a right. We'll need a mid, and we'll need mid. We're gonna generate at each level. We'll need the input and then the target. So here we're going to. So let's don't forget to call that. So we'll call BST, and then we'll pass in the left, the right, and then the nums, and then the target. Down here, we're going to generate the mid. This will be the same. This will be pretty much the same formula that that I talked to you guys about earlier, which will be right minus left divided by 2. Okay. So now the next thing is, let's go ahead and so we need to make sure that the left and the right, you know, it doesn't. So we only want to run the inside of these if our initial like base case kind of fits. Else, we would run into a base case where we essentially run out of things to search. So we could return -1 here. I believe. Let's see. And then here we'll do target. Sorry, if nums I equal target, then we could return that. Let's go ahead and return. Sorry, this is min, and then we could return min. Else if, and this will be the same. If is less than the target. And then here's the other else case. And here is where we just recursively call our function, but the only trick is we pass in essentially pass in our left and right as one of the mid value, +1 or -1. So here we could return the BST of, let's see, left, if the mid, the current mid is, alright, hopefully I don't mess up again. Alright, so left, right, +1, sorry, mid +1, and then nums, and then the target. Let's fix this guy right here. Turn BST, right, -1, left, oh sorry, mid. Oops. This should be mid -1, and then right, and then nums and the target. Yeah, so if you look at this code, it's very similar, right? So just to run through what the code is doing is here I'm initializing like my variables that I'll be working with. So this will be my lower bound and then my upper bound, and I'm calling this function BST and passing in all the variables that I need. Here I'm using that same formula to generate the mid value, the mid index, and then here I check to see that my left and my right hasn't met, because this is essentially my base case, right? So if they have met, then I could just return 1, because then we have exhausted our entire array. But if it's the case where it's still the left bound is lower than the right bound, then the first thing I want to do is I want to check the mid value, the current mid value, the index, at that index, is that number equal to our target? If it is, then I could just say, hey, I found the value, return that index. The next thing is the same thing that we did before, where if this is where we're splitting, like essentially cutting the input size in half, upper bound or lower bound, depending on this. Let's go ahead and run it. Oh, I have a typo here. Okay. Oh, max cost that? Okay, I think I got it. I made 2 mistakes. One is I swapped these around again. I'm sorry about that. But it's easy to debug. And then also, I was essentially going like lower and lower, which is the opposite of what I wanted to do. So let's go ahead and run that. Looks like that worked. And it was accepted. So great. So yeah, I hope you guys enjoyed that problem. It's actually one of my favorite algorithms that I learned a while ago, and it kind of opened my eyes to like, oh, you know, the programs that we write, they're not all equal. It's one of the algorithms that really got me to start thinking about Big O and the importance of it, right? Because before I would just like write code and I would just like do whatever I can to make that piece of code like run and execute and give me an output that you want. But you know, like I said, not all programs are equal, and I hope you guys start thinking about these kind of topics, and it's extremely fun. So just keep chugging along these problems, and I hope you guys will ace your next coding interview. I was actually asked this problem in like a hidden form, at least in 2 interviews. And you'll use actually this problem to solve like more difficult problems. Like for example, there's a problem called threesum, which uses binary search as one part of the algorithm, for example. But yeah, so I hope you guys enjoy this problem, and I'll see you guys on the next one. Bye.